So let's get started. So Carlos again here, and Demerval. So we are working on this project to build LLVM with glibc with LLVM. So I'll give you a quick introduction. So the goals here for us is to build glibc with a different compiler other than GCC. So initially for both x86-64 and AR64. Also improve the glibc code coverage by using these different warnings from LLVM. Improve clang support for features that are directly tied to glibc, but not necessarily glibc compiler support, like the 45 headers. And check for performance difference between the compilers, like in generic math code, for example. So the problem is that glibc uses the GNU-C standard, so a lot of GNU extensions in the code. The same thing is true for the static linker assembler. So glibc expects to be neutils. Some of the GNU extensions that we need were already discussed with the LLVM community, and they will not take it, like the nested function support. And we also have the problem with compatibility between the compilers, like for float 128, for example. So, Demerval.
So, thank you. To give some history, this project was done initially over multiple releases without a defined plan. It started with a Google engineer, Feng Song Hui, that approached us with the idea to first enable glibc to build with LLVM LLD, and he put some patches to deintegrate the GNU build from being neutral, so he can use a different linker. And then he approached us with some more work to disable or optimize some stuff by removing GNU extensions like nest functions. And then we found out multiple problems when I actually tried to, let's see what happens if I try to build glibc with LLVM. And then it was a work with multiple releases to check what we need to either implement on LLVM or we need to re-implement on glibc to get this done. The nest function was the first one. If you not know, nested functions was a GCC extensions, and it has some problems. If you try to take the function address, sometimes the compiler needs to do an executable stack, and it is a security issue. And LLVM said, no, we are not going to implement it. So we had to re-implement it, and we worked this on glibc. There is another, this as label function after first use. It's something that a very specific LLM issue that glibc headers use internally to do some optimizations, and we had to rework because it was very GCC specific. So this is all this GNU-C extension that glibc uses that are very tied to GCC that we had to rework, rethink, to adapt on how to do on glibc. There's other minor issue which has some being neutral optimizations for some specific reallocations that LLD also initially didn't implement it, but over the releases they decided to implement it. There's another issue on the loader that we have disjointed reallocation sections that it's another issue that LLD initially tried to overcome by restructuring glibc, and then when we fix it, they also implement this on LLD. And there's a, There's another more broad project, more sub-project where we need to actually restructure the glibc code because some specific feature rely on a compiler flag that does not make sense to implement it somewhere else than GCC, and this requires to reorganize a lot of code. Another thing that LLD initially didn't implement was to use a linker script. They end up re-implementing this later, but on the version that we start to work, we had to use this version script to add some hardening feature, and then we went up rewrite some code to avoid this, and it was in the end a very nice thing because it cleaned up a lot of old code. We had also to change some assembly directives because the way that Clang does, it does not use Minutus internally. It has an integrated assembly where it itself tries to parse the assembly directives, like either if you compile an assembly source or an inline assembly, and it does not implement all the support that GNU GAS provides you. So we had to just use a more specific or a more compatible option, and it also leads us to improve the Clang support while you use with glibc. Doing this work, we found out that some Fortify headers shows a lot of issues, and it turned out that although the current glibc Fortify support is compatible with Clang, it does not implement all the Fortify support that we'd like to, because it relies on GCC extensions that Clang implement differently. So we basically rewrite the Fortify Clang support, and it was on the latest release. So now probably if you use Clang with glibc, you get this new Fortify if you're compiling new code. And although this is still work on an out-of-branch in the official repository, we are slowly getting the pieces upstream. There is a lot of stuff still that requires for only to build it, glibc, for both x86 and ARM64. 1/3 is to enable the build, 2/3 is to build all the required test cases. Otherwise, we don't see how is the difference between the coverage. And we also support all the new configure options that people are enabled recently. For instance, we have this enable Fortify source, which we enable Fortify for the glibc itself. So we have like some memcopy, memset, string routines. We have this enable CAT with a new Intel option to use the control execution. I don't recall the last bit. We have the enable memory tagging for ARM v8.5. And all this stuff, we are targeting a minimum glibc LLVM version 16. But I think it's possible to build with old release, but we decided to start with the 16. So the current status is, besides the compiler itself, glibc requires some GCC runtime to enable some support for pthread, backtrace, and other stuff. And then this is a problem because the way that LLVM project is organized, it's a slightly different than the GCC one. So you need some specific compiler CMake LLVM configuration to enable runtime that is that's similar to what GCC provides. But if you run with a GCC runtime, currently we see a very minimal regressions, meaning a very specific corner case. Most failures come from the MAD code, which has some specific differences on how GCC handle floating point exceptions that we need to adjust on LLVM. But the bootstrap is still not that easy as we do for GCC. Another limitation that we have is some iFun corner cases. We are not very concerned about this because iFun it's now not that widespread, although recent GCC it's using on function multiversion. But this is a very specific case, corner cases that I think it's not used on code generation by GCC. We have this Gmon, it's an old way of profiling things that we have a different ABI between ARM64 and GCC. There is an easy fix either on GCC, on LLVM or on glibc. I need to find out where exactly we're going to propose the solution. As I said, some MAD tests show some wrong code generation, but are most limited to long double float 128 for ARM64. And I think the thing that will require most work is how to provide a way to bootstrap a toolchain without GCC runtimes. And this what this LLVM Glibc runtime helps us. It was a new LLVM sub-project proposed by Google. It's already upstream, where they built a library similar to what GCC provides using LLVM runtime. I started to check the current status. There's a lot of issues with this project, at least for glibc, but it can run most of the test cases and it shows somewhat good results.
So I'll talk a bit about the problems in the LLVM runtime. So like Norval said, we need libgcc for floating points, also for long double and float 128, unwinding operation backtrace, and ptragic installation. So glibc expects the libgcc.so library to provide some symbols like GCC personality, the problem is that the LLVM runtime does not provide all those symbols. So like libwide doesn't support GCC personality. That's the symbol that's missing. So like he said, we have LLVM libgcc, which is basically a new way of packing the compile-RT and libwide code. So it creates essentially a libgcc from LLVM code, but it's missing a lot of things. Like it doesn't provide the means to handle software floating point exceptions. It supports only one routing mode for floating point. And another big problem is that all the symbols are public. So with libgcc, they are hidden, and that will generate a lot of PLT calls and for any soft float calls. So there's a lot of work to be done there if you want to use that for bootstrapping. And we have an issue open, which is public. You can access that show the current status of the build of libgcc, LLVM libgcc, and we have 96 regressions for x86-64 and a bunch more for AR64. So for future work that needs to be done, so we need to upstream the first part of this port to enable the build with LLVM for AR64 and x86-64. We think it should work for 32-bit ARM and 32-bit x86, but that might be a stretch, I don't know. We need to upstream also the fix for the test cases, fix all the regressions caused by the compatibility between LLVM libgcc and glibc, and also add that to the CIs to avoid any regressions that may arise from either the LLVM side and glibc side. So that's all that we have. So questions?
Hi. On the point you made about ifuncs, whilst they're not heavily used today, the reason that we've implemented function multi-versioning in both tool chains is that we see this as a route to unlock new architecture features in environments where you have to assume a basis of like V8 such as, Android and things. If we hope that the use of this will go up significantly now that it's supported in toolchains. So if that's not working here and you need it for deployments, then you might want to, at some point, consider fixing those issues.
Yeah, so if I recall correctly, the main problem that we found is some user cases that are not well defined, like if you have a PIC object linked against a non-PIC object, and you have a hidden CBON that calls a non-hidden CBON. How is the linker we're going to handle these cases? And if the process is a PI, no PI, and how you combine hidden. So it's not the usual way.
Okay.
It's we have a bunch of these cases that are, in fact, are very being user specific. It was coded for x86 initially and extended to the other architectures to follow what x86 does for these very specific corner cases. But as I said, that I think it does not actually touch the way that functional multiversion is done, because the default case with global symbols, it works as expected.
Okay, well, cool.
Nobody else?
Okay.
Okay, thank you.
Thank you.